So, in the last lecture we saw the spectral theorem for finite dimensional case, that is, if you have a normal matrix, there is an orthonormal basis with respect to which that normal matrix looks like a diagonal matrix, right. So, there are certain things which I did not emphasize on because these are things which you are supposed to know if you are attending this course. The eigenvalues, the eigenvectors corresponding to distinct eigenvalues are orthogonal, and the whole space decomposes into orthogonal direct sum of eigenspaces, right. And on each eigenspace the matrix is very simple, it is just multiplication by that particular eigenvalue, right. That is how the operator looks like. So, it reduces to a very simple form. Essentially the same thing happens if you go to higher dimensions, that is infinite dimensional Hilbert spaces, assuming that the operator you are looking at is a compact normal operator. So, we will first assume that it is a compact self adjoint operator, and remember the exercise from the finite dimensional case which said that if you have a normal matrix, it is self adjoint if and only if the spectrum or the set of eigenvalues is contained in the reals, right. That means, it has only real eigenvalues. So, we will see, of course, the same thing continues to be true in the case of infinite dimensional Hilbert spaces, and we will do the spectral theorem for compact self adjoint operators on an infinite dimensional Hilbert space, and then extend it to normal operators. Okay. So, let us start. So, first we start with compact operators. Compact operators. So, the script h is going to be always a infinite dimensional complex separable Hilbert space. Separable Hilbert spaces. Many things I say will be true for real Hilbert spaces, non-separable Hilbert spaces and all that, but we will not be bothering about any of that. Okay. Whenever I say Hilbert space, it is going to be a complex separable Hilbert space. It may be infinite dimensional or finite dimensional, but it is always a complex separable Hilbert space. Okay. And T from H to H is a bounded linear operator. Okay. So, T is said to be compact. So, let me define this for you. Again, this is something which you are supposed to know, but we will do a quick recap, right. T is said to be compact if T of H1. So, what is H1? H1 is going to be the closed unit ball in the Hilbert space H, its closure is compact, where H1 is all those vectors V in script H whose norm is less than or equal to 1, right. So, norm V is less than or equal to 1. Okay. So, you look at the image. So, it is a bounded set because it is a bounded linear operator. Take the closure and you want it to be a compact set in the Hilbert space. Remember, these are infinite dimensional. So, closed and boundedness need not imply compactness, right. You have seen those examples. Okay. So, some of the facts you should know about compact operators in general, I will state it down. Okay. So, facts. Okay. One, if so, this collection of compact operators is closed, right, in the space of bounded operators on H. So, you have this operator norm, and if you have T n which are compact operators converging to T in the operator norm, then the limit is also going to be a compact operator. So, if T n are compact operators and T n converges to T in the operator norm, in the operator norm, that means norm of Tn minus T goes to 0, right, then T is compact, then T is compact. 2, T is compact if and only if T star is compact. The adjoint of T defined using the inner product and so on will also be compact if and only if there exists a sequence of finite rank operators Tn such that Tn converges to T, right, in the operator norm, right. That means any compact operator can be approximated by a sequence of finite rank operators. Okay, so let us go to the next page. Let's see if okay. So, third fact, let this is important, let T be a self adjoint operator So, what is self adjoint? That is T equal to T star, right. Then, so if T is a self adjoint operator, then the norm of T, that is the operator norm, this is the supremum of norm T H, right, the inner product with norm H equal to 1. Right. If you look at T x y and then take x and y running over the unit ball, of course, you will get the norm T. But if you have a self adjoint operator, then it is enough to look at these diagonal kind of elements, right. T H H are kind of diagonal elements. Okay. So, 4 T is compact if and only if whenever x n converges to x weakly. Okay. What does that mean? Convergence weakly means x n inner product with y converges to x inner product with y for every y, right, in your Hilbert space, right. That is what you mean by weak convergence, right. So, T is compact if and only whenever x n converges to x weakly, we have the image under T, that is T x n, should converge to T x strongly, right. So, in the norm, right, goes to 0. In particular, so this is more important for applications. In particular, if x n is a norm bounded sequence, that means norm of x n's form a bounded right supremum norm of x n is finite, then supremum norm x n is finite, then of course, you have a weakly convergent subsequence of that, right. And so, if I apply T to it, I will have a strongly convergent subsequence. Okay. So, then we have a convergent subsequence for T x n, right, because x n there is a subsequence x n k which converges weakly and so T x n k will converge strongly. Okay. So, these are some facts about the compact operators which we will use. Okay. So, before we write down spectral theorem for compact self adjoint operators, let us have some useful propositions. Okay. So, let me write it down here. Proposition: if T is a compact operator on H, so if you go back to what we did in the last lecture, the proof of the spectral theorem dependent on the fact that we have eigenvalues, right. So, we managed to get an eigenvalue using the fundamental theorem of algebra, and that was an advantage in the case of finite dimensional situation. Here we have an infinite dimensional situation, and then you can't say that eigenvalues exist. So, you have to prove that they exist, and this proposition will essentially allow us to show that certain eigenvalues exist, okay, when under the assumption that the operator is compact. Okay. So, if T is a compact operator, okay, on H. So, remember H is always a separable Hilbert space. In this case, it is an infinite dimensional complex separable Hilbert space, and for some lambda in the complex plane, let us say lambda not equal to 0, we have infimum of. So, this is going to be a condition to say that lambda is an eigenvalue. Okay. So, norm of T minus lambda acting on H, where H runs on the unit sphere, norm H equal to 1 is equal to 0. Okay. So, what is that saying? T minus lambda acting on the vector H, right. So, where is H? H is running on the unit sphere in the Hilbert space H, right. If that infimum is 0, of course, if lambda is an eigenvalue, which we already know, let us say, then there is a vector H naught such that T H naught equal to lambda H naught, and H naught I can take it to be having norm 1. Then this infimum is already 0, right. We are saying if the infimum is 0, then we do not know if any element is 0, but even then we can say that lambda is an eigenvalue, provided that we have a compact operator. Then lambda is an eigenvalue for T, okay. That is, there exists x in H such that T x equal to lambda x. Of course, in that case the infimum of this quantity we are looking at is obviously 0. So, this is sort of a converse of what we have. Okay. So, let us see. Okay. So, we will try to prove this proposition. So, proof. So, this is going to be the first step in the proof of the spectral theorem. Okay. This tells me a condition under which I can say that eigenvalues exist, which means to produce an eigenvalue one can use this proposition, and we will see that when T is a self adjoint compact self adjoint operator, either the norm of T or minus or the negative norm of T is an eigenvalue. That is sort of easy from the finite dimensional case. You should be able to guess that is what is happening, because if I have a finite dimensional matrix and I have a diagonal matrix, then the norm of the matrix is the supremum of the norm of the modulus of the eigenvalues, right. And so that is one of the eigenvalues, and that is precisely what is happening here as well. If T is going to be self adjoint, then either the norm T or negative norm T will be an eigenvalue for T, provided T is compact. Okay. So, let us prove this proposition. First of all, there exists a sequence of unit vectors because I am looking at some infimum of something, right. Infimum is 0, that is what I am looking at. So, I can take a sequence Hn, sequence of unit vectors Hn such that that particular quantity goes to 0, right. So, unit vectors Hn such that norm of T minus lambda acting on Hn goes to 0, right, because the infimum is 0. Okay. Now, where are Hns? Hns are unit vectors. So, that is a sequence of bounded, right. So, it is a bounded sequence, and so when I apply T to it, that bounded sequence, I should be able to get a convergence subsequence because T is compact, right. So, now Hn is bounded, T is compact, right, we know that, and so if I apply, so hence there exists a vector x in my Hilbert space such that, and a subsequence, right. So, and a subsequence T Hn k, right. Hn is bounded. So, I apply T to it and I get a subsequence which converges, right, minus x T x n k such that T Hn k minus x goes to 0. Okay. All right. So, okay. Now, write a slight manipulation needed here. Hn k equal to lambda inverse. So, remember lambda is not 0. So, I can take lambda inverse lambda minus T Hn k plus T Hn k. Okay. I am not doing anything non-trivial here. If you look at what is there in the bracket, T Hn k and minus T Hn k gets cancelled, and I will have lambda times Hn k and I will lambda inverse, right. So, this is simply Hn k. But what is the advantage of writing this? What happens to this? I know that the Hn was a sequence such that something went to 0, right. So, this goes to 0, right, lambda minus T acting on Hn k goes to 0, right. And what happened to T Hn k? Because of this, whatever we have just written here, T Hn k goes to x, right. So, Hn k goes to, so this will go to lambda inverse times x, right. The first term goes to 0, second term goes to x, and there is a lambda inverse outside. Okay, very nice. So, now also norm Hn k equal to 1 implies x lambda inverse x also has norm 1, implies x is non-zero, right. I want to say x is the eigenvector. So, I do not want it to be 0, right. All right, since Hn k converges to lambda inverse x, right, that is what we have in this step. T Hn k, where will it go? It will go to lambda inverse into Tx. Okay. But we started with T Hn k converging to x, right, but T Hn k converges to x, hence whatever is here and here should be same, Tx equal to lambda x, right. So, that proves that x is a eigenvector for T with eigenvalue lambda, right. So, hence, so lambda is an eigenvalue for T, right. So, that is how you find eigenvalues for a compact operator. Okay. So, let us write down the spectral theorem. So, spectral theorem for compact self adjoint operators. Okay. So, we will be looking at compact and self adjoint in the beginning, and then we will go to normal operators afterwards. So, recall that T from H to H is said to be self adjoint if T star is equal to T, right, and normal if T star T equal to T T star, right. So, let me write down the full theorem. So, instead of writing saying that there is an orthonormal basis and with respect to which it is diagonal, let us write down this in a slightly formal language. Of course, we will say what are eigenvalues and so on, but there are several properties which one should note, which are automatically true in some sense in the case of finite dimensional situation. Okay. So, let T be compact and self adjoint. Okay. On H. Then, so let me write this as 3 or 4 parts. T has only countably many distinct eigenvalues. Okay. So, the eigenvalues of T, there are only countably many. It can be finite. Okay. It can be a finite rank operator, for example, the range can be finite, and you may have only finitely many eigenvalues, and you may have a huge kernel, that can happen. But otherwise also it can have only countably many distinct eigenvalues. Okay. 2, if lambda not equal to 0 is an eigenvalue for T, the space, so the corresponding eigenspace for lambda will be finite dimensional. So, the space kernel of T minus lambda, right. So, what is this? This is the corresponding eigenspace, right, where T acts like lambda, okay, is finite dimensional. Okay. 3, if well, they are also real, right. So, because it is self adjoint, I should have said that in the beginning. T has countably many distinct eigenvalues and they are real. Okay. Because it is self adjoint, right. So, eigenvalues have to be real. Okay. So, if lambda 1, lambda 2, lambda 3 etc. are distinct eigenvalues of T. So, there are only countably many. So, I can write them as lambda 1, lambda 2 and so on, comma Pn the orthogonal projection onto kernel of T minus lambda n, right, that is the corresponding eigenspace. So, you look at one eigenvalue lambda n, look at the orthogonal, so that is a finite dimensional space, subspace, so it is closed, and to that finite dimensional space there is an orthogonal projection which we denote by Pn. Okay. Then these Pn's are so yeah, let me go to the next page. Then the Pn's are orthogonal to each other, that means then Pn Pm equal to Pm Pn equal to 0 if n and m are different. if n is not equal to m, right, because they project onto orthogonal subspaces. So, in the finite dimensional case, this simply says that if I have, or even in the infinite dimensional case, it simply says that if I have distinct eigenvalues, the eigenspaces corresponding to these eigenvalues are orthogonal to each other. Okay. That is what is written in terms of the projection onto those spaces. The projections, if you multiply, you get 0 is same as saying these spaces are orthogonal to each other. And the most important part, after the fact that there are only countably many eigenvalues, each lambda n is real. Okay, so that I had already included, and the operator T, so that is my compact self adjoint operator, is actually a sum of these projections, right, n equal to 1 to infinity. So, that is an infinite sum of operators. So, I should tell you what it means, right. So, this simply means that limit k going to infinity summation n equal to 1 to k lambda n p n, right. So, each thing on the right hand side n equal to 1 to k lambda n p n is an operator, right. You are simply adding up finitely many operators, and the convergence convergence is in the operator norm. Convergence in the operator norm. Okay. So, that is the full statement of the spectral theorem. Okay. So, let me repeat, we have let me show the statement fully, so that it is clear. If T is a self adjoint compact operator on the Hilbert space H, it has only countably many distinct eigenvalues, okay, and they are all real because I am assuming self adjointness. If lambda not equal to 0 is an eigenvalue, that means the non-zero eigenspaces are all finite dimensional. Okay. Lambda not equal to 0 is important, it can have a very huge kernel, right. Like you can take any compact operator, any compact operator and add a huge 0 operator to it, right, and you will still have a, like take a direct sum, you will still have a compact operator. So, the space corresponding to 0 can be, the space corresponding to 0 need not exist, but if it exists it can be huge, it can be finite dimensional or infinite dimensional. But if you look at a non-zero eigenvalue and the corresponding eigenspace will have to be finite dimensional. Third is if you take the distinct eigenvalues, then the corresponding eigenspaces are orthogonal to each other, and we have the operator T to be a limit of finite rank operators, where this finite rank operators are precisely those projection to the eigenspaces and multiplied with appropriate eigenvalues, right. That is how it will look like. The operator T on kernel of T minus lambda n looks like multiplication by lambda n, just like what we have seen in the case of matrices, and when you add up you get a finite rank operator, and that as you keep on adding up will converge to the original operator in the operator norm. Okay. So, that is a strong statement. Okay. So, let me stop with a proposition. So, well, we if possible we will prove all that, otherwise we will complete in the next lecture. Okay. So, proposition. So, we will use these results to prove the spectral theorem, and the proof of the spectral theorem is going to be essentially the same as what we saw in the case of finite dimensional case, except that existence of eigenvalue as an issue will be an issue here, right. In the other case existence of eigenvalue was very easy. Okay. So, proposition. So, there are three parts to it. If A is a normal operator, and lambda is a complex number, then kernel of A minus lambda is equal to kernel of A minus lambda star. So, we have seen this in the case of finite dimensional situation, right. If I take something from kernel of A minus lambda, that is A v equal to lambda v, then A star v equal to lambda bar v, right. And kernel of A minus lambda is a reducing subspace for A, right. That is, what does reducing mean? Reducing means that is invariant under A and A star, right. That is what we did, right. So, if you remember, the first step in this finite dimensional spectral theorem was we looked at an eigenvector v 1 and then showed that A v 1 equal to lambda 1 v 1 implies A star v 1 equal to lambda 1 bar v 1. That is precisely what is written here. And so, the orthogonal complement, the space and the orthogonal complement becomes invariant under A and A star. That is precisely the reducing property. Okay. So, if A is normal and lambda mu are distinct eigenvalues for A. So, we are not assuming any compactness here, okay. These are properties of normal operators, okay. Eigenvalues. So, we do not know eigenvalues exist or not, okay. If lambda and mu are distinct eigenvalues for A, then they are orthogonal, okay. So, the corresponding eigenspaces are orthogonal to each other. So, kernel of A minus lambda is orthogonal to kernel of A minus mu, okay. Eigenspaces corresponding to lambda and mu are orthogonal to each other. One more, see, if A equal to A star, and so that means it is self adjoint, and lambda is an eigenvalue for A, then lambda is real, okay. So, once it is self adjoint, the eigenvalues are real, okay. So, let us just read it again, the three things which we will need in the proof of spectral theorem. Here there are there is no assumption of compactness, right. These are general properties of normal or self adjoint operators which we will require. So, first says that if A is a normal operator, then the kernel of A minus lambda and kernel of A minus lambda star are same, right. That is the eigenspace. So, if A acts like lambda somewhere, A star has to act like lambda bar, okay. That is all it says. If A is normal, then the eigenspaces corresponding to distinct eigenvalues are orthogonal to each other, and if A is self adjoint, any eigenvalue is going to be real, okay. So, that is how well we will prove this in the next class. So, for the time being we will stop, okay.